Failing. Bro. How are you not on my board? There you go. All right.
Out there. Out. There we go.
Somebody should stream it to people in here, maybe?
Yes. All right. Hello and welcome. Hello. Just getting everything queued up here. Co-host, multi-guest. One of these things has to work, right? Invite. Awesome cat. Shane. All right, gentlemen, bear with us here while we get this going.
Bro, I can see you went to the phone style for the stream format.
For the phone lads, bro.
Yeah, no, that's great, except
yeah,
I set up my whole thing with your other one, and now my whole scene is fucked. So, so what I'm streaming is right now the top of your forehead and the bottom half of your desktop.
Oh, that's super unfortunate. Okay, hold on.
All right, I'll fix it. No, it's fine. It's fine. Leave it. It's
no. I have to do this anyway for the YouTube thing. Otherwise, they can't actually see what's going on here.
Okay.
So this will be. This works. Okay. All right. All right, so as people start filing in here, go ahead and tag your favorite globularist. We're going to break down the celestial theodolite and have a little back and forth with anyone who wants to understand it better or has any questions.
Who wants to throw a grievous insult in the form of argumentation on you or whatever. However you guys do it.
However you guys want to do it. All right, so how does this work? So mute, invite.
All right. I fixed it. I did it. I'm just going to put this over here. All right. It's messy but workable.
Thank you, Kat, for encouraging the viewers to share the stream. See if I can move myself over a little bit. There we go. Very cool.
We have a guest on stage.
Nice.
Okay, so you believe in the earth being flat, so you're like fucking retarded? Like, oh my god, how do you...
Yeah, no thank you.
Oh, how quickly execute. Nicely done.
Yeah.
I can't see who's on stage. That's crazy.
So the interface looks different than it used to on phone mode, yes. So I'm not sure.
That's what I'm saying, I guess. All right, so who's the panel?
I don't know.
Nope, that's not it.
The multi-guy?
So, like, what would have happened if you didn't ice that guy? Is that would have been trolled for like a full minute as I struggled to find where the button to axe him is.
Oh, there's the panel. Okay, I found it. I remember how this works now. Your mic's kind of bouncing back and forth as you're like juggling it for some reason. I just don't understand why you're like juggling it.
I'm
You're like,
not. I'm
does it?
holding it though.
Why can you not? Are you like caressing it?
Dude, it's so small to see the text that I have to pick it up and look at it.
You're like, oh, you're the most beautiful microphone in the world.
It's my phone, dude. I gotta pick up the phone.
Oh, yeah, it's really rough on the ears. All right, cool. So we're going to get started here in a few. So remember, tag your favorite globularist. We're going to go over the celestial theodolite. Actually, while that's going on, I will download the PDFs from me.
Yo, for me, it puts the chat right over your face. So all I can see is white text
On your YouTube?
on TikTok, which now gets pushed to my YouTube.
Should I move? So I should move the chat then, you're saying?
Yeah.
Gotcha.
You should move it. Oh, can you move it just up a little bit? That would be good.
I can make it a little smaller. How's that?
Is it in a different spot for you than it is everybody else?
I don't know.
Did we lose Cat?
We lost Cat. She's back.
I'm back, gentlemen.
Welcome back.
All right.
All right. So what's the situation with the chat? Can I move it back or is it still messed up? Is it independent of where I place it?
Yeah, you didn't do anything to it.
Okay, cool. Fantastic. So it's not a me issue.
We have a guest on the panel.
Welcome, BDW40 thrice.
What's up?
What's up, my man?
What do you guys talk about?
Well, we're about to go over the celestial theodolite and present a new and exciting flat Earth evidence.
What is the theodolite?
Ooh, it's a great question. Theodolite is an instrument that you look through, has a little reticule in it, and you make angle measurements with it. So basically, you just kind of look out horizontally, and you're looking for things to go above or below your little horizontal line there.
I see. Kind of like one of those compasses you look through with a clino on it.
Like a sextant. Yep. Exactly.
Interesting.
Exactly. So they use it for surveying specifically, and they'll say things like, well, if I look through my theodolite and I look at this mountain peak, based on the globe Earth prediction, it should be at this angle, if we were to math it out. And, when you take measurements during the day, there's refraction conditions. And Taylor, she recently pointed out a paper where they talk about how refraction can fluctuate mountains in the distance by up to, what was it, like 25, was it 10 to 15 arc minutes, something like that, which is a very significant amount. And so what the celestial
10 to 15 minutes
arc minutes, yeah. So it's just like how much the angle would
forever.
increase.
How long of a distance?
For hers, I think it was 100 miles, I think.
That's interesting.
Yeah, it's pretty intense. So the way that we're going to propose, which was given to us by a guy named Dr. Mike Heffron, is a method where you take the measurement at night using the time in which a star gets occluded by a mountain peak. So because the mountain it has to be the physical object blocking the star, we can take the timing in which it was blocked and measure and get the angle of the star with stellarium and see if we can confirm like a flat Earth prediction versus a globe Earth prediction for the actual elevation angle, irrespective of refractive conditions.
That's a pretty good idea.
Yeah, it's dope. Okay. Well, I think we got enough people in here, so we'll go ahead and get to it. Let me break this down here. So if you can see on the screen share right now, what we're looking at is beyond the null hypothesis. And we're going to keep it real simple here. We're all familiar with the scientific method. We have a hypothesis and a null hypothesis. Can you mute, please, while we're going through? Thank you. Unless you have a question or something. And anyway, so our null hypothesis is going to be the Earth is flat, and we're going to try and falsify that. And then our alternative hypothesis is going to be the Earth is a globe. So we're going to do two separate calculations and see, and then take a timing measurement and see which angle we get. It's either going to be the raw flat Earth angle, uncorrected of refraction, just plain trigonometry, or it's going to be the globular prediction, which has globe slant and refraction cooked into it, so that the angle, that's what's going to make the angle differences, essentially. So we have two separate mutually exclusive outcomes to determine evidence for flat or globe. So that's what that looks like there. So flat, globe. There's going to be globe slant here that's going to make this mountain peak lower relative to this observer here. So we're going to see how this plays out. So we're going to use Pikes Peak, for example, and we're going to go 50 kilometers away from Pikes Peak. This is the top here, the observatory, or the observer center on top of Pikes Peak there. And we have the latitude and longitude and distance from the observer, 50 kilometers, and we have the final bearing. So what we can do with this information for Pikes Peak is we can get the accurate elevation angle from GPS, or Wikipedia has, like, everything that Mike did was done from the information from Wikipedia in in like a GPS app on his phone. And my buddy recently went deep and did the ECI to ECEF transformations to confirm all the elevation angles. Everything all checked out, is good to go. So using this methodology, you can get the accurate predictions to what they would say is down to the down to the wavelength for GPS. So anyway, we have the information here to establish the what we need to make our prediction here. So once we have our elevation, we're going to subtract the elevation from our observer point from the elevation peak of the mountain, and that's going to give us 2,226 meters above sea level. And we got our distance here. So now we can trig that out for our angle, which comes out to be 2 degrees and 31 arc minutes for the raw calculation there. Let's see. Okay, so this is just how to math out the prediction to get the tangent for it. Or theta, sorry. Okay, so this is the globe Earth refraction prediction for celestial refraction. This adds 15 arc minutes to an observation, so this will be important for the globular prediction here in a second. Oh, Shane, while I'm doing this, can you send me the Google spreadsheet link? We'll go over that here in a second. Okay, so any way you want to chop this hypothesis, the Earth's a globe, the Earth's not a globe, whatever, you can chop it up any way you want it. So here, the significance of this. Now remember, we're not interested in taking an actual theodolite and measuring this angle during the day, right? Because it's going to give varying results. We already went over that earlier with the refraction stuff. So what we're going to be doing is measuring the timing that a star gets blocked. Why is this important? Well, it's important because the physical object is what blocks the light. So we're not concerned with where this apparent star is, where it is after the measurement, etc. Right? We're only concerned at what time it gets blocked when we can no longer see it because it's physically blocked by this mountain peak. We're only concerned with that time. And when we take that measurement, the implication at that timing to create that intersection for that mountain peak is that if you were an observer standing on the mountain peak at that exact time it gets occluded, you would instantaneously have this exact angle for that intersection, and that's the flat Earth prediction. So the globe, what we're going to go over here in a second. The globe here, 1 second, I'm going to hit this water. The globe makes two separate predictions. The first prediction the globe makes is the elevation angle based off of globe slant. So if you do the arc sine, which is basically taking the distance, the same distance that we took earlier for the flat Earth prediction, and then just dividing it by Earth's radius, that's going to give you the globe off slant, or the globe slant, which is going to offset this peak by about 220 something meters, which reduces it down to 2 degrees and 19 arc minutes. So remember, the flat Earth prediction raw was 2 degrees 31. The globe predicts the intersection timing for this is 2 degrees and 19 arc minutes, and that's after you add the 15 arc minute refraction to it to make the prediction. The actual calculation comes out to be 2 degrees 4 arc minutes, but we give them the refraction or whatever. It doesn't matter. We can do both. And then on the top of the peak here, what they would predict at that timing would be that the star would be at 246 with refraction instead of 231. Okay, so flat globe. Okay, so if it's a flat Earth, then this horizontal plane then it extends on for the measurement. If it's a globe, then there's going to be 2 separate angles here, and the timing in which this gets blocked is going to be longer than the flat Earth prediction. It'll take more time because the star has to get lower in the horizon to get blocked by this. So we're going to predict an earlier timing versus a later timing. And then a second peak was done, but we can come back to that. We can just stick to the Pikes Peak. But this was also confirmed with another peak and 6 different stars that were occluded by this, confirming the timing for the corresponding angle to show the same relationship that we have shown here with this triangle here. But anyway, okay, so now we'll go over the actual measurement. So the star 39 Aquarii was measured at 6 p.m., 6:27:25 p.m. Mountain Time. And that's when the star got blocked by the mountain peak. So by taking time-lapse footage every 1 second, even if you add plus or minus 1 second for accuracy or air tolerance, what have you, that's not going to increase it large enough to make oh, maybe it's the globe prediction. The globe timing offset would be based off of that distance would be like 16 to 18 seconds later. So instead of 25, it would be like, in the 30s, 40s. So it's not going to be at that same timing. And this is the important part of this measurement, this time right here, because this is the prediction for a flat Earth to make this corresponding angle. That is the important relationship that we're establishing for this angle, because how the globularist will argue this is they'll say, oh, you know what we need to do? We need to put an observer on the top of this and take a measurement at the same time. That's not what we're doing here. You wouldn't predict the same angle. You're moving 50 kilometers closer to look at the thing it's not even analogous. You're taking it too far. This is very, very simple. This is only about the time the star isn't seen. So when we see the star, we don't care. We don't care where it is. We don't care where it's at. If we're standing on the peak, we only care if we can see the star when we're right here on the ground. And then when we can't see it anymore, we want to know what time it is. And then from that, we can measure the angle. That'll give us the corresponding angle. Then we can go into stellarium. We could use our final bearing information that we got earlier from our lat long stuff, and then we can figure out the angle prediction if it matches or not. So that's how that works. Now we'll go over a little spreadsheet here to kind of break this down a little further. And if anyone has any questions, or I'm not able to see the mod thing, so if anyone's been requesting or anything like that, go ahead and toss them up.
Yeah, good. I just started checking. Nobody's here. Dude, why am I echoing?
Fantastic. You might have
Are you
something.
sharing audio?
You might have something
I will
open.
approve any requests, and I will let you know as they join the panel. So
Thank you.
When is this measurement taking place?
Oh, that goes over. Oh, I see how. 1 second.
January 29th, 6:30 p.m., I think. This year?
Yeah. I see what you mean by the text going over my face now. I didn't realize that it was okay.
Yep.
Yep, totally. So I can actually just swap. Nah, it's fine. Don't care. Fix it later. Okay.
By that you mean
But exactly.
and nobody, it'll be text on your face forever. It's
Exactly.
Fine. It's fine.
Yes, sir. So to answer your question, that was done on the 1st of the year, on the 31st at 6:27:25.
All right, thanks.
Yep. And quick little backstory: this observation came from somebody who was a glober, and they got into taking theodolite measurements because they wanted to help out a friend of ours, Taylor, who was making her own theodolite measurements, and she was getting kind of bamboozled a little bit by the globularist. And this guy was like, you know what, I'm going to take some measurements and do some analysis and help Taylor out. And what he found that at this time, this is when at that exact time is when he became a flat earther, because that's when he was like, oh, that's this is what this means. It's the implication there. And then he went and did it, replicated it with different stars and different peaks. And yeah,
He went to Blue Mountain, Cheyenne Mountain, Mount Rosa, Pikes Peak, Lone Pike Peak, and Blodgett Peak.
Oh, you got them all. Nice.
So this was done in multiple locations.
Yeah, multiple locations at different times, different days. And then we're trying to get people to replicate it. So we're trying to educate people on how to do it and get interest in it so that they can come and learn how to do it themselves, and they can start making these observations. Because the thing with this is that this completely eliminates the argument of refraction. Like, the only way the globularists have been able to argue this is has been explicitly by misunderstanding it aggressively, or in straw manning it. What actually needs to happen is they need to make their own measurements of stars being included at times that correspond to the predictions that they make based on globe slant and the actual physical peak being at that location, because it's physically tilted away from you relative to their position. And they haven't even attempted to do that. They've only attacked the measurements and introduced things that aren't our predictions or part of what we're putting forward to try and answer it. So yeah, like, once more people understand this and start doing it, like, this is hugely significant, because the only thing you need to do for this is have a way to take a time lapse and, like, have binoculars. Like, you don't need an expensive theodolite. You don't need anything crazy. You can do all the calculations with software and various websites that are given to us here. Like, everything you need can be done with, relatively cheap, and with an error margin of plus or minus 1 second. All you need is your time. Your phone will do. It's synced to GPS time. So, yeah, it's pretty
So what did
significant.
the data come out saying?
Flat. Everything that he
Wouldn't
measured.
you know it, dude?
Yeah, everything he measured gives the elevation angle for the flat Earth prediction. Meaning.
So
Yeah, go ahead.
the testable part about it is you put the GPS long lat of the obscured mountain peak into Stellarium. It doesn't actually know where you are. Obviously, you're within visual seeing distance of that mountain peak, but Stellarium has no idea where you are on the Earth. Yet, for every observer that has the same occluding time, angle works for all of them. So it's a pretty solid proof every single time.
See, I went on a couple of these panels just see if somebody could answer my question. I'll get to that in a minute, but nobody wanted to answer it, and they just tried to belittle my intelligence. It was nuts. I don't know. They're kind of rude. You guys seem intelligent and respectful.
What was your question, sir? We might be able to help you out.
Yep. I was wondering why the shadow of the eclipse moved the opposite way it should have last year during the solar eclipse of April.
Dude, that's a very good question, except it always moves in the weird direction and nobody ever explains it. Right? Here's
the way I put it. Like, they're trying to tell me, sorry about my daughter's blowing my phone up. They try to tell me that it was caused by the moon's orbital velocity, because it's traveling at twice the amount of what Earth is supposedly spinning at. But they give me all these numbers. They're like, oh, there's kind of big numbers being thrown at you all at once. I'm like, all right, I'll get back on here after I plug all these numbers into an equation. So in order for that, it can't be the orbital velocity of the moon, because it's moving. Say if you put a laser beam on the moon and aimed it down at Earth, like stop the rotation of the Earth, and you aim that laser, that moon is moving 38 miles an hour.
No, the moon is moving like.
Well, I mean, the moon's shadow would be moving 38 miles an hour from the moon's orbital velocity, because it takes 27 and a half days to complete one cycle. And it's moving at 2288 miles per hour. You know what I mean?
2288. Yeah, that sounds about right. I don't have the numbers. That sounds about right. Yeah.
So you take the circumference of the Earth, which is 24,901, and you divide that by 27.3.
Nope.
That'll give you 912 miles per day. Divide that by 24, gives you 38 miles an hour.
No. Oh, yeah. Okay, I see what you're saying.
You see what I'm saying? And it's moving.
Shane, we have Pearl and Katie didn't know it on the board with us now too. So we've got 3 guests here speaking.
Nice, thank you. Welcome everyone.
Still in hostess, kid.
But do you guys follow me?
No, say it again.
No.
Like there's trying to say that since the moon is moving almost twice the speed as the Earth spins, and they're both going in the same direction, that the reason the shadow is moving that way is caused by the moon orbital speed, which is wrong. Yes.
No,
so you understand?
It's not wrong.
Wait. So are they saying it goes back? It's like drifting backwards. It looks like, or whatever. Is that kind of what you're saying?
Yeah, the moon orbits eastward. The moon orbits eastward. If you to make it simpler, it's easier if we just use the Earth frame of reference. So in Earth's frame of reference, the sun is going west and the moon is going west more slowly. And as the sun overtakes the moon, the shadow moves from west to east.
Yeah, but it's only going 38 miles an hour, and the Earth spins it 1,038. So the movement of the shadow is caused by the rotation of the Earth, is what I'm trying to get at.
No, I mean, yeah, that's
well,
part of it.
Yeah, but it comes up in the east all the time, every time. The only way that it moves in the opposite direction is during an eclipse.
It doesn't move in the opposite direction during an eclipse.
All right. Well, we'll have to come back to that one because we're kind of trying to stay on topic for the thing. Sorry, we don't have it. Sorry. No,
you asked me what my question was.
No, you're good. You're good. Don't have an answer for you on that one. Have to think about it some more. But Parole, did you happen to, or Katie, did you have any thoughts on the celestial theodolite?
It sounds like I don't know why you wouldn't just use a theodolite.
Great question. So we're trying to determine whether or not the elevation angle, or that the elevation of the peak of the mountain as measured by theodolites from a distance is actually accurate due to Earth curvature or refractive conditions. We're trying to distinguish predictions here. And so using the timing that a star gets blocked, we can actually determine the physical elevation angle, like the correctness of it, independent of trying to measure it with the theodolite ourselves. Because actually, I can just go ahead and tell you, during the day, the mountain measures close to what the globe predicts, like within an arc minute for sure. It's like it measures like 219 during the day. Absolutely. But the thing is that it gets occluded. The star gets occluded at night at the angle that corresponds to 2 degrees 31 arc minutes. So we're saying that, like, refraction, optical conditions, optical compression, due to atmospheric conditions, etc., are what is affecting the measurements during the day. But the globe seems to be completely created out of that, because otherwise, if that mountain was actually at an angle to us and like it was missing elevation to relative to our position to it because of that, then the star would get blocked at a different timing. It's
Yeah, I totally agree. And I say it all the time whenever I'm up in panel and in these discussions that they don't have effects of a curve. It's atmospheric conditions, right? Either that the visual horizon or apparent horizon, due to refraction, can either measure like further or shorter than the actual physical horizon, like the distance that you're seeing. So it plays it, and it attributes to the ramping up of the horizon on top of, I'd imagine, perspective causing it to come up. So
absolutely. So check this out real quick in regards to refraction and how it makes up the difference here. So when we look at the spreadsheet, we have the raw flat Earth prediction on the left here, which comes out to be 2 degrees 31 arc minutes, and then the globe prediction accounting for globe slant comes out to be they actually remove 27 arc minutes from their prediction, so they come down to 2 degrees and 3 arc minutes for their raw calculation, assuming Earth's radius of 3959. And then we added the celestial refraction correction to give them 15 arc minutes, so that puts them at 2 degrees and 19 arc minutes. Now, when they take when they do their occlusion timing, when the star gets occluded and they're instantaneously teleported to the peak like we are, their prediction they have to add another 15 arc minutes for refraction. And that puts them at 2 degrees 46 arc minutes. And that difference from the observer on the ground to the peak is the missing globe slant. It's 20, which is made up in refraction. So the globe literally only exists in this celestial refraction correction.
Yep. They one of the guys who he's not a surveyor, but he got a theodolite just to make measurements. He's a glober, Mike Snow. I'm not sure if you're familiar, and he had commented that in one of my lives that he's always had to invoke refraction. So of course, you're never going to have no atmospheric effects, and it's just it's an illusionary curve, so to speak.
Well, just so we're clear, right? The celestial theodolite's a concept, and we're applying it, right? We have the eyepiece is the you the observer making the observation through a telescope or binoculars or theodolite scope, whatever you want, and then we have a horizontal crosshair component of this theoretical tool being the mountaintop that we're using to physically occlude an observable star at night, and then we have the vertical crosshair where we confirm that calculated elevation angle using, say, stellarium or any astronomy tool of choice. So those things together, that'll give us our celestial theodolite concept. So we're looking through an actual optic from our position. We're making an observation of a physical mountain peak, which is our horizontal, including the star. We get our vertical crosshair being our confirmed elevation angle in stellarium. So that's the celestial theodolite concept, right?
And I've got a question about the reciprocal zenith angle. I hear a lot of the globe believers bring up this reciprocal zenith angle, like that's supposed to prove their curvature somehow.
Shane is a reciprocal zenith angle expert. Shane, you want to? My man just set you up for a pre-dunk, bro. You want to kick the field goal home and put it in the net or whatever you do?
Dude, due to a sports ball thing or a metaphor? Is that what you're trying to tee off over there? Dude, yeah, reciprocal zenith angles as a function of optics would definitely be subject to the same atmospheric refraction and atmospheric opacity and those sort of opaque qualities that we were just going over, but they're actually more so specifically at the elevation with which they typically take normal reciprocal zenith angles measurement. I have a paper over here that cites there's like a margin of error that they replicated with their reciprocal zenith angle setup at the specific altitude. That was a variation of like 6 arc minutes or something huge, something well beyond the margin of error with which they were proving said, theoretical excess. So I got to find that paper and I can bring it up. But I know that I showed that to Ruhif and he never brought it up to us again. There's also a couple other observations that you can make with refraction being a key component, being the actual cause of the deviation for which they use it to prove said curvature.
Yeah, all you gotta do, it's crazy, is just actually look for it. What affects reciprocal zenith angles? And so because of the ramping up of the horizon, yeah, it's atmospheric. Oh, sorry, dang it, it doesn't. But if you can still get an idea, right? Atmospheric conditions between two of the observation points, temperature gradients, pressure variance, and humidity. Then that's all. I didn't type in a leading question, and I looked more into it, and I was like, well, of course it is. Even if the horizon's not ramping up to eye level, it's still coming up. So of course you're going to have a greater than 180 degrees total. So it's that simple. It's all it's atmospheric conditions, light, creating this illusionary curve.
And then, right, mathematically, if you're looking linearly off into a flat plane and you have linear compression as you would on a flat plane, up to 100 miles, it's visually indistinguishable from, say, the trigonometric curvature of a sphere, which is also indistinguishable from the parabolic curvature of 8 inches per mile squared derived, right? So those three are indistinguishable optically at the surface level up to 100 miles. So that's why they get all mixed up, and they claim that actually what we see as you would expect to see on a flat plane is actually because you live on a sphere, and that's the whole trick.
Love it when they say the horizon can't happen on a flat plane, and I'm like, you realize that a plane is a tangent to your ball, and is only one point on that ball is like everything else is below that plane, that tangent. So what do you mean it can't come up? Like, what?
Dude, how funny is it that they're like, we can tangent anywhere on a sphere, but it doesn't work on a flat Earth though.
Yeah, like you can't actually have there should be no horizon on flat Earth. I should be able to see China from my back porch, and the sun should never set. Those are all three part of the same argument, right? That's goofy.
Yeah. Light doesn't travel forever in our atmosphere. Light is scattered and absorbed. And number two, the sun's not actually going below the physical horizon. What's more, that horizon ramps up. So even when it starts to disappear behind that apparent horizon, in actuality, it's still above the physical horizon. I'm like, it's not even going below the horizon. Like, geez.
Which is why we took that same instrument and we applied it to the stars, and we removed the key component for them to dither or digger or whatever you want to call it, and then we're using it as a weapon right now, right? So that's why we have this challenge out there, this component. We can use it as a celestial marker. We can incorporate a mountain to have a physical star being included, and we can say, hey, the angle that it's being included only works on a flat plane, and we can predict it with perfect plane trigonometry. So what up? What up?
Yeah, thank you, Shane, for making it on Strange World last night.
Yeah, that was fun, dude. I didn't know that there was so many cool people in the comments of that show. I was reading the comments later. I was like, wow, dude, no one called me a faggot. No one said it was terrible or whatever.
Oh, easy, bro. Easy on the F-bomb.
Oh, yeah, right. Yeah, the context was weird. Like, dude, everyone was super supportive in that.
Yeah, and their whole location thing, the longitude and latitude lines. Now, granted, they always fall respective to certain places, right? But because of continental drift, which destroys the globe, right? They distance apart. I know it's not much, but just in the last 40 years, right? So let's say Hawaii moves 4 inches a year. So that's like what, in 40 years time, I think that factored out to about 13 feet. That's still significant, because what happens on their ball? Everything just comes right back into it. But yeah, not to mention that the stars still line up celestial navigation with certain places over the lands. So how does that, there's just so many things. And they just seem to think, oh no, that's okay, it's fine. I don't get it.
Where did our Glober go? We lost our one Glober.
We lost our one Glober, but did you have anything to add about the longitude stuff, Shane? She was talking about? Longies?
What are they talking about? Converging meridians?
Yeah, you were just talking about that last night on Strange World, weren't you?
Yeah,
the measurement of converging meridians on the ground.
So I don't think that you can measure converging meridians on the ground. You can, however, reify it to the same symmetry in the southern sky, right? Because if converging meridians, they're not really like physical lines. A longitude line isn't something that you see or marker. It's based on the sky. It's based on, the timing of the sky specifically. And so the sky looks the same in the south as it would in the north. If you're trying to measure symmetry and distance between theoretical skylines, that's the only way you'd make it match. So therefore, the only way you could, quote, measure would be to appeal to GPS, the longitude, latitude, the actual graticule, any of the corrections to said, coordinate systems, any of the astrogeodetic connections, any of those wouldn't be measurements of the ground. They'd be reifications of the coordinate system measurement.
An important thing to note on using GPS for the confirmation too, they have meridian corrections built into the timing, like for their timing correction. So it's always going to match whatever the globe or not the globe, whatever the coordinate system that it's using, which is the latitude longitude system. It's always going to match no matter what, because they literally add or delete time. So, so. It would, you just walk right into the endless reification.
Yeah, so they claim that they measured this, but I'm almost, I'm willing to bet what they did was compare it to some sort of coordinate system, some geodetic survey, some GPS go, look, it confirms that in the south, the longitude lines get smaller according to my map, right? Mm-hmm. Unless it's not that, in which case I'll refute it.
Nope.
Hola.
What up, man?
So you guys believe in you trust longitude and latitude lines, right? Yes or no? I just need to know if that's true or not, because then the point I'm making won't work.
When you say trust, like, what do you mean? Can you use the latitude longitude system to navigate and reference places and traverse to calculate distances
Correct.
between things? Yes.
No, of course.
Okay. Cool. So, did you know that, whether or not we can't go there, I don't care about that, the center of Antarctica at 90 degrees latitude has an infinite amount of coordinates. Did you know that?
Did not know.
Yeah. You mean on a flat Earth splayed around the outside edge and the AE projection? Sure.
So that's the point. So on the Gleason map, it doesn't work. So the flat Earth cannot work with that.
Right. Solid point. Flat Earth debunked. You nailed it. Never thought about it like that, dude. Actually, wow.
I mean, that does debunk,
dude, honestly,
completely.
Yeah, no, you're absolutely right. And the authoritative tone in which you said it from your chest earns my respect even more.
So I can show you. I don't have to tell you. I can show you.
You're gonna show me an AE map? No way. Do you have one on you?
AE map? What's an AE map?
An azimuthal equidistant direction preserving projection home slice. The thing you're talking about, right? The thing that you're trying to debunk.
What in the hell is that?
Well, it's a type of orthographic projection when you're trying to project a projected coordinate system known as cosmography. Have you not looked into maps or?
A projected projection.
A projected coordinate system, dude.
You said projected projection.
Projected coordinate system is what it is.
Okay, so first of all, longitudinal lines, they converge on the southern hemisphere.
Do you think that they're physically converging on the ground? Could you show me a measurement of that?
So on the globe, like on a map.
How would you measure it?
So on a map, when we measure latitude and longitude, okay, the lines have to converge because the distances between both longitudes at the equator is 69 miles, but then when you get lower than the equator, they start to get closer together. That's objectively true. Whether or not it's a sphere or not, I don't care.
Then no, that's a geometric property of a sphere. But okay.
But that's the thing. That only does work on a sphere. But I'm talking objectively speaking. Whether let's say I didn't know the shape of the Earth, and I looked up longitudinal lines because I know that people use them to navigate, and I saw that two longitudinal lines. Let's fucking go with prime meridian and I don't know the longitude 1. I saw that they are 69 miles apart at the equator, but then on the south part, if I go to like Chile in South America, right? Or if I go in that section in the southern hemisphere, that it's not 69 miles apart anymore on my navigation system. Why is that? So my brain says, like you said, that could only work on a sphere, not a flat Earth.
Brilliant. That's a brilliant deduction. You proved it by looking at your phone, you said, right?
Nope. I'm actually looking at SpaceAudits' face right now on my phone.
Well,
I can show you.
So, the evidence.
I'm literally right here laying on a couch, not looking at anything.
I'm with you. Solid evidence. I appreciate it.
It is solid evidence. You believe in coordinate systems. They only work spherically.
No, it's completely silly. That's a completely silly interpretation.
Again, when you go in the southern hemisphere, each longitude line gets closer as you go south. That's just a fact. I don't care what shape you think it is. They get closer together. Why are you laughing? I'm telling you objective truth. You can look this up. Google it.
I'm laughing because you make statements like, this specific geometric property that only happens on a sphere will happen, and I don't care what shape it is. Meaning you made a declarative statement about a specific parameter of a shape, and then you declared that it applies to all shapes. I didn't make a specific
parameter about a shape. But anyway, I made a specific parameter about navigation systems.
You're talking about a measurement that you're not actually confirming. You're not taking any first-hand measurement.
I am talking about.
You're going down there.
Can confirm.
And you're looking at the coordinate system projected on your favorite graticule. In this case, would be the sphere.
Dude, when you say big words,
courtesy of Google Earth,
just to let you know,
or your GPS system, or whatever you're looking at, is just going to confirm where you are in the first place, right? So the spherical coordinate system being confirmed by the spherical coordinate system measurement doesn't actually prove the shape of the Earth. In fact, it's not related to the shape of the Earth at all. Latitude, longitude itself is from the celestial angles, right? Latitude synonymous with the angle of Polaris in the north. Of course, you have the same relationship in the south. Longitude gets converted via time. The time a star appears over the Earth via the right angle hour transformation, right? So you do 15 degrees per hour, and you can get 15 degrees multiplied out to convert those two spherical coordinate systems. Doesn't actually measure the Earth at any point.
Okay, so are you done? Because that was a lot of stuff, and you kind of said the same thing I said, and then you're concluding that it's flat. You said the same thing I said, that they converge on a navigational system, right?
Yeah, the spherical coordinate system that we believe in.
It's a coordinate.
We did not say the same thing you said.
It's a coordinate system.
We use spherical coordinate systems. Why are you thinking it's flat?
If you were to map out two hemispheres and you had to merge them together to make a single unified coordinate system, what shape would two hemispheres merged together make? It would complete a spherical coordinate system. We're saying that, you see, you're muted. Because you're talking over people. I don't know. So listen, what we're saying here, right? You're using the coordinate system itself to reify the shape of the Earth. That's the thing that's in contention, right? We have evidence to provide that will give us the correct interpretation of the coordinate system that we're using, because we agree that the coordinate system itself is spherical, right? And it can be projected onto a globe. It can be projected onto an AE map. All these things. Yes, it can. That is a primary feature of it.
Yeah,
yes.
sorry.
Yeah,
yes,
you're good. You're good.
Projected.
Yes.
Okay.
So we're trying to figure out what's the most accurate interpretation of the topography of the ground in relation to this spherical coordinate system, which is just represented by angles to the stars. Now, would you like to examine some other evidence outside of just reifying or arguing through the coordinate system itself? Because that line of
angles to the star, angle to Polaris. Yeah, 69 miles. Every 1 degree latitude you go, it's going to be 69 miles.
Cool. So are you familiar with a fundamental plane in celestial navigation, astronomy, etc.?
No, I don't know what that means.
Okay, so it's this intersection point of these two hemispheres that they say that they have, right? One would be
I wonder why they say it, but keep going.
Yeah, right. Well, they need a flat baseline. So you mentioned angles of the stars earlier. Did you happen to catch the celestial theodolite prezi that I was giving earlier? Oh, your mic's muted. 1 second. Unmute.
Can you stop muting me? I don't talk over people.
You're good, man. Continue.
Jesus Christ. So I've never seen you work with the theodolite. No.
Okay. Well, I haven't theodolited personally. It's a concept that was measured that we can lay out for how to take a measurement of the timing in which a star gets occluded based off of a flat Earth prediction or a globe Earth prediction. So doing a little trig and using a mountain peak of Pikes Peak, we can determine, like using just plain trigonometry, what the raw angle would be for the elevation of that peak by subtracting the elevation of the observer and then the distance to the peak from the observer, which would give us a raw angle of 2 degrees and 31 arc minutes. When you do the same thing on the globe, when you do the arc sine of that and divide by the Earth radius, you get 2 degrees and 4 arc minutes, and then you add refraction for 15 arc minutes, which takes us up to 219 arc minutes. And then if you were at the peak of this mountain at the time that the star gets occluded, you would predict, because you have to add another 15 arc minutes for refraction at the top of the peak, you predict 2 degrees and 46 arc minutes. So we have two mutually exclusive predictions on how we can determine whether or not angles of the stars are defined by the hypothetical fundamental plane that intersects, that goes on in perpetuity for everything, or if Earth's radius is a factor and these angles to the stars show a relationship to that. Because if there is a relationship to Earth curvature and angles to the stars, what will happen is, because we're 50.7 kilometers away from this mountain peak, it's going to be tilted away from us. And there's going to be about 220 something meters missing from the peak of this, and that's what's creating the angle offset. So if we were going to measure the timing in which a star gets occluded, the star for a flat Earth would get occluded faster than a star for a globe. It would take more time because it has to get lower in the horizon to get to that peak. So what was actually measured and confirmed was, one second, scrolling through here.
Debunker, he said, sorry, I'm just answering a question. Debunker, he said that's refraction, which, no, but keep going.
Oh, okay. Yeah, one second. Well, we can continue or we can go back to the refraction corrections here in a second. So on January 31st, 2025 at 6:27:25 p.m., the star 39 Aquarii was intersected by the Pikes Peak mountain peak here, which we'll look at the screenshot here. At that timing. So if you do plus or minus 1 second for air tolerance, the globe still predicts, based off of it being 2:19, it would be about like 16 to 18 seconds later. So this, mutually exclusive timing here. And then this was reproduced at another peak with multiple stars as well. So you can do this anywhere, and it shows the correction angle for the stars. I'm sorry, it shows that the raw angle is with respect to a flat baseline.
So that was a lot of stuff, and I commend you for doing math and actually doing a lot of work there. You're different than a lot of people. The problem you're having, though, is you're measuring from one spot, and the latitude goes down south. So every latitude you go, it's still going to be the same angle.
So like I said,
sorry, it's going to drop 1 degree angle. I'm sorry, that was stupid of me. It's going to drop exactly 1 degree every 69 miles. Always.
Yeah, so that's going to be it. So what would be in contention is this an optical effect for the star displacement relative to your latitude, or is this due to Earth curvature relative to the latitude? So this is how we can determine. This would we'll see if it was Earth curvature. Then though, this mountain would be occluded at a different time. I mean, the star would be occluded at a different time. So this is actually mutually exclusive to us.
Sorry, what does the mountain have to do with the star?
It's literally the crosshair, right?
Great question. So if we're looking at this image here, you can kind of see this little theodolite on the ground and this lad looking at the theodolite. So what we would be doing here by using the star as the crosshair, when we can no longer see its light because it's being blocked physically by the peak here, when it gets blocked, we know that it physically blocked it. So now we have an angle on which we could draw a straight line to show this. So instead of measuring the angle between these 2 points like this, we're using the timing in which this gets blocked to confirm this angle independent of refraction. And Barron asked how we calculated all this. He wants to see the calculations for it.
I kind of do too, because we literally did this in a book that showed the a ship looking for a White House over the curvature, and the book was published and done with the correct math, and we tested the math ourselves. I was there with Barron, and they were correct. So I don't think that the book would actually agree with you. I don't know where you did this, but
the way that we do this, oh crap. We're eliminating refraction by using the mountain as the crosshair, right? When the mountain physically occludes it, it removes refraction. Chill out, homie.
Hold on a second. Sorry, I'm getting messages. Hold on a second.
I would say it has to be optical. No, sorry.
Huh?
With the angle to Polaris, because especially considering with your continental drift, I'm sorry, I'm just on this lately because it just absolutely annihilates the globe. But so with the land shifting and moving over time, granted the coordinate systems have remained respective to certain locations, but so lands have moved right? Just even over the 40 years, the last 40 years, but over time, and yet you have this perfect angle to Polaris from each line of latitude in the northern hemisphere. Like it's got to be optical because otherwise that's doesn't work out.
The sky didn't move, right? So nothing would change, irrespective of the land, because that's how the coordinate system works, right? It used to be called cosmography, so it has almost nothing to do with the land, as it turns out. The only thing that they try to tie it to is the spherical datum through their geodetic surveys, which ties it to ellipsoid and WGS-84, etc.
So real quick, Baron from the chat says we can't preclude refraction. We can't ignore it.
Baron is a land surveyor.
Yep, he certainly is. So check this out. We absolutely can, and the reason we can do that is because when the star is gone, right? It's no longer being refracted up above it. So we don't care where the star is at that time, right? We care about when we can't see it anymore. When we can't see it anymore, it's no longer being refracted up. It's gone. So that at that timing, right, that's going to be at a specific, that's going to show a specific angle, which is going to correspond to when it gets physically blocked. That is the significance of it. So it's not that we're ignoring refraction or we don't believe in refraction or anything like that. It's this observation specifically eliminates refraction and tells us the elevation of that peak because it's when we can no longer see it relative to our distance away from it.
Yeah.
What you're not getting though is that if the Earth's flat, first of all, Polaris doesn't move. We know that, right? You know, the Polaris doesn't move.
It oscillates in a little tiny circle, but try and stick to the
I'm sorry.
point.
Yes, it does do that. I'm sorry. I was being. I don't. Yeah. Okay, you're right. It moves and there are star trails, but you understand that on a flat plane, the further back you go, Polaris is still going to remain high up, and you would be able, for example, if I'm on a flat. Oh, I thought I had a plate down here.
No, it equals your latitude. Polaris elevation equals your latitude in the northern hemisphere, right? Literally, your elevation angle will equal your latitude. How high it appears to be perspective induced is what creates the latitude. But we're specifically arguing about this celestial theodolite observation and measurement. Are you saying that you're conceding to this and you want to move to perspective based on Polaris as an argument, or what?
Well, I'm saying that let's say right here is Polaris. If I'm looking at, okay, let's say this picture of, this guy's a streamer, by the way. His name's Scoop Dog. He's really cool. So let's say he's Polaris. Okay, I'm looking up from the Earth, which you considered as flat, this table. If I'm moving this way, okay, my angle's not 69 degrees anymore. If I'm all the way over here, it's not 69 degrees. It's always, 69 miles. Fucking hell. Sorry, I'm tired. So it's not 69 miles in order to keep 69, in order to keep a linear equation, right? If it's dropping 1 degree every 69 miles, it doesn't become a linear equation. It doesn't drop 1 degree over here. It drops like 100 degrees at some point, the further out you go. But it always drops 1 degree every 69 miles. If you're going 69 miles, right, we agree it drops 1 degree every 69 miles, but if you go 69 miles over here, it doesn't drop a degree. It drops, like I said, 30 degrees. That's speculation, I'm not being exact. So that's why it doesn't work on a flat Earth, because it'll drop a lot further over here.
Right, but once more, that is optical. That's the point I was making with how, the coordinates are.
But I'm not talking optical.
Well, right, yeah, but you are.
You are though. You're looking at it, and we're So listen. Let me tell you a few problems here, right? So primarily, the problem with what you're putting forward is you're assuming Euclidean geometry and parallel light rays from a light source at X amount, or like an infinite distance, essentially, right? And you're saying it would only be possible for these stars' positions to deviate if the contour of the Earth, changes at 8 inches per mile squared, which leads to 69 miles per degree, which means that when you're 69 miles from where you previously were, you're going to see that star change by 1 degree in the sky, right? You're saying that that's the physical
The star changes 1 degree every 69 miles.
Right.
If you go 69 miles at one point on a flat Earth, it won't be 1 degree.
Ooh, so here's the thing. We have an entire spreadsheet on curved visual space in our azimuthal dome of vision, and our assertion is that optically there's an equivalence there. So because everything in the sky is apparent, we all see in our own azimuthal dome of vision, then the equivalence there is the same.
You're getting into what's subjective.
Hold on, no. Hold on 1 second.
Right.
It's not subjective, right? We see do we see forever? Can you look across the sky and see, or can you look across the ocean and see like England or something like that from New York?
Well, if the Earth were flat, I mean, you probably could.
No, you would have to have unlimited resolution. Even hang on, how do I make you smaller here? All right, even if you're so think about what you're putting forward, right? You're saying like you have a monitor that's 1080p, right? And you could fit, let's say, like 1 pixel, of information per app you open up, right?
I'm sorry, I'm going to stop you for a second. It doesn't work the same way with monitors. I'm sorry. I got to interrupt you. This monitor is very different.
No. Just listen though. You can only fit so much information in, is what I'm saying. You're saying that you're just going to fit in like infinite information forever in the same finite spot. It's not even tenable on both. In both models, there's atmospheric conditions. There's a visibility index.
Okay,
so it's not even.
Sorry, that's not the same thing with the pixels. Do not work the same way as our eyesight at all.
It's a analogous between.
I know what you're trying to do.
Resolution limit.
If you can find another analogy, that'd be great. But that's not a good one because pixels don't work the same way as our eyesight at all.
So you're saying that you could fit unlimited things into your eyesight then?
I mean, technically, yeah, but we wouldn't see it very well. We'd have to zoom in. We'd have to zoom in to see it. You can't zoom in. If you digitally zoom in on a picture with a monitor, the pixels start to block.
I got you. So I see why you don't accept the analogy. We're at a fundamental impasse on that. So yeah, we won't be able to proceed any further.
If you could find another analogy, that would work. But you can't use a monitor. Is all I'm saying.
No. Perspective and ground curvature is a crazy argument, dude. The actual angle, right? We should go back to the celestial theodolite, what you're trying to get across.
Yeah, we'll go back to the celestial theodolite. But
don't go back to the celestial.
Hold on, real quick.
With you, I didn't really understand your reasoning behind the celestial theodolite because it all has to do with the fact that no matter what. Like we can talk about perspective, we can talk about like what we're seeing or what we see in the sky. The star is dropping 1 degree. And if we go 69 miles at some point all the way in Chile, okay, it's still not Chile. If we go 69 miles all the way to the equator in Ecuador, right? It's still going to be 69 miles. But if you go to Ecuador on a flat Earth, on a flat map, it won't be 1 degree. It'll probably still be pretty high actually, because it's not really, on a flat Earth, it's actually only 3950 miles, but not 6,200. Because the circumference we can still agree with is 24,900, right? Do you agree with that or no?
Yeah, that's what's given to us. That's what's represented by the Laddie lounges.
Right.
Yeah, we're good.
Right.
But to get us back on track here, because what you're asserting though is circular, and we're at the point where we're at the same impasse that we were earlier, where we have to move to something else to verify externally which interpretation is correct. Because you're saying that's only possible due to Earth curvature, right? Which okay, fair enough. And I'm saying that it's an optical effect, so we're gonna have to. How do we rectify the two? We can't keep reifying each other's positions, so we're gonna have to move back to something else, and that's where I would introduce the celestial theodolite again and try and help you understand the significance of that measurement better. Because otherwise, we're just going in a circle. Because if I'm correct about the optics, then it doesn't matter because we're going to perceive it the same way. So the significance of this measurement, it tells us what the baseline elevation angle is for all these stars. Because Stellarium uses the nautical almanac, and that's what. So it's going to tell us like, is this derived from a flat baseline, or is this corresponding to where the globe would predict it is? So that's the globe. That's the significance of this.
But Stellarium uses a globe.
Well, so when you have refraction on, it's using the globe, right? You can turn refraction off, and it actually shows that's how that.
We talk about the same map. Stellarium looks at the stars.
Yeah.
So up. No, refraction is. We're not talking refraction here. There's no horizon we're looking at.
There's celestial refraction, my man.
Oh, sure.
Yeah, that's what. Well, when you use Stellarium,
I mean,
okay. It's default on Stellarium, and that's what makes the globe predictions. So anyway, you can toggle those on and off to see. If you toggle it off, right, it matches the flat Earth baseline prediction for the angle for when the star gets occluded at that specific timing, which is detrimental to the globe because if the Earth were a globe, it would get occluded at a different time. So this is so what this means is, irrespective of how you conceptualize 69 miles per degree happening, it's everything that you're referencing for the stars was derived from a flat baseline, because you can go anywhere and do these measurements with these stars using the flat raw prediction and get that timing.
No, sorry, Katie. You can talk if you want. Oh, okay. Baron can explain the celestial theodolite. I've never heard of that. Baron, is that a real thing?
A celestial theodolite? No.
Okay, that's what I thought. But,
hold on. It's a concept. We've been over that. It's not a real thing. We told you explicitly it's a concept.
It's a concept. I didn't hear you say that.
Yeah, we're using the timing in which the star gets occluded to verify the angle measurement. So instead of using like a little theodolite to measure the thing, we're seeing like, can we see the star? Oh, we can't see it anymore. What time was it when it got blocked? Oh, it got blocked at that time. Okay, let me pull up Stellarium and see what angle it would have been at that time. Oh,
you don't need to pull up Stellarium to do that though. You could just keep using the theodolite, right, Baron?
Anyway, we need to know the angle in which the star was occluded at, and then it'll match the angle that that we predicted.
Oh, so where did Baron go?
So when you defer to Baron, doesn't know the argument for the celestial theodolite, to ask him,
I don't know what happened, man.
Doesn't really help.
He works with theodolites. That's why, man. I've never done that. Actually, there's a phone app you can get too.
So what is the question?
Well, my question to Space Audits is I don't understand how he said it's a theorized appliance, a celestial theodolite.
Okay,
I'm just wondering how that works.
Can you pull one up on Google and like show me a picture of it?
No, it's not. He said it's a concept, right? You said it's not a thing yet.
It's a concept.
So how are you measuring things with a concept?
With a clock. We're measuring the time it gets blocked. We're looking at it with either binoculars, theodolite, telescope, recording device. Huh?
Who's we? Who is we?
Dude, why are you being weird? A man specifically named Michael Heffron specifically.
Okay.
Is that? Are you?
Well, no, I thought
are you good?
You were part of this or something like this.
Okay.
So you were saying we, right?
Yeah. So anyway, the measurement is made with timing. When we can't see the star anymore, that means that we're using the physical elevation angle of that mountain peak as the crosshair to intersect with that star, which is going to tell us a specific angle that corresponds to that timing.
What is the distance?
What's that?
The whole concept is we made predictions using trig on our spreadsheet, right? We had a corresponding section for the globe prediction incorporating said globe refraction, right?
I'm asking you for the distance.
Well, so we were 50.7 kilometers away from the observation, which is what we used to plug into the actual elevation.
Hold on a second. Baron, if you're going to do that every time we're speaking,
he's very butthurt since our last engagement, I think.
Just in perpetuity, know that we're referring to Michael Heffron, if that makes it easier to save us time from you doing that every time. Anyway, continue, Shane. And if you do it again, you can just leave because that's annoying as fuck.
Dude, we calculated a flat Earth elevation angle using our planar trigonometric calculation at 2 degrees 31 arc minutes. Now, when we put our location to that mountaintop in Stellarium, as I have open here right now, as a matter of fact, you can put in that star, 39 Aquarius, you can put yourself to that time, 129 at about 6:30. This past 2025, January 29th, and you can look for this star and you'll see that the actual angle for that star to be occluded at this time, because this is the time we saw it occluded, is 2 degrees 31 arc minutes. And if I turn on atmospheric refraction, it pops back to the quote apparent location, which is 2 degrees 46 arc minutes, which is the globe quote prediction. So the difference between globe and flat Earth in this prediction is refraction, right?
I got you up on the big screen if you want to show it real quick.
Yeah. Let me do
show
camera.
It for the boys.
Yep.
Baron,
so
do you,
here's 39 Aquarium.
Baron, do you have Discord or a way to exchange like your calculations and stuff off of TikTok, like a convenient way to message you?
No, I just do TikTok.
Gotcha.
So my location is Pikes Peak over here. I'm at this latitude and longitude, which we already sorted out. 125 at this
I wasn't here
time.
for that, so I'm just asking.
Well, and then we have this angle. Well, I'm just assume that everything we're telling you is correct because you've been over it 4 times, so we can catch you up with the argument.
I know, but I wasn't
to make
here.
the actual argument. I know that's right.
I'm just asking you with the distance. Where was the instrument set up, and what's the distance to the peak?
We're specifically taking the time to break it down for you, right? So you could help us out by not interrupting with the questions. We would like to answer your questions,
you
right?
Distance, man. That's all I'm asking.
50.7 kilometers.
Okay, 50.7 kilometers. Okay.
Yep. So then when we're just confirming in stellarium, right? 2 degrees, 31 arc minutes. This is without atmospheric refraction on. This is confirming our planar trig elevation angle, right? From our spreadsheet over here, doing basic trig to confirm that this final elevation.
I'm going to work it out right now.
Cool.
And if you like, I can share my camera and kind of walk you through how to do it.
Ooh, can you do an ECI to ECF transformation to be double extra GPS sure?
Yeah, I mean, we could do a Rhinex file right now if you want.
Yes, let's do that. Let's get the most accurate methodology done.
Yeah. So what was the observation height?
He was at... We just used his thing at sea level at 50 kilometers away. Give me 1 second. I can look up what it is.
Observer altitude 2,074 meters. Peak altitude 796 meters.
2,074 meters. And it was Pikes Peak, which is 14,115 feet.
Yep. All right. While you're calculating it out, I can bring you up on the thing if you wanna share.
Yeah. So I actually have a Pikes Peak measurement.
Nice.
We can go over that right now, actually. So here, this was from Saturday, March 9th, 2004. I was in Rush, Colorado.
Mm-hmm.
This is the height of my instrument. I was 5,740 feet above sea level. The distance was approximately 54 miles. This was inversing both coordinates at each end of the line. And this was Pikes Peak elevation. This is what I predicted. You can tell me if this math is correct, Shane. Shane, are you there?
Is that measurements during the day?
Correct.
Oh yeah. We'll pretty. So I'll throw you a bone too. So check this out. Mike's original measurement.
Are these correct?
I'm sure. Yeah, I'm sure it is.
No, I mean, can you do the math real quick and just make sure?
I'm sure it's fine, bro.
No, I want to make sure that we're all on the same page.
Do you want me to get my triangle calculator out and plug it in for you, bro? I trust you. You can proceed forward.
Okay. So this would be the angle on a flat Earth, right?
Is it? What did you just do the elevation minus the elevation of the peak to get the difference?
No. So here's my elevation here.
Mm-hmm.
Right. Here's the peak.
Mm-hmm.
This is the difference in elevation here.
Yeah.
This is the arctan of that. So would this be flat Earth?
For their prediction at that elevation.
Yeah, I mean, if the Earth is flat, here's your baseline. I mean, it's a pretty straight up deal, right?
I mean, at that elevation, sure.
Okay.
It's the same thing we did because with Mike's distance and elevation, it's the same thing. It looks the same.
So here's what I measured.
Okay. You measured that during the day, yeah?
Yeah.
Okay. So the significance of what we're putting forward is that there's optical effects during the day, different refractions, and we'll have or different refractive effects. And we'll have Taylor come on and break that down from a paper that she just read recently about this exact thing for measurements during the day. So the significance of this is that the time that the star gets occluded at night, right? It's not going to get occluded by a refracted image. It's the physical thing that's blocking it when we can no longer see it. So the difference between what is measured during the day and what is measured at night with that star angle is the significance in how we're removing the optical effects that happen between us and the mountain during the day when we're taking that measurement that's going to cause that compression that's going to make that globular prediction. Because like Mike, when Mike did the measurements with his theodolite to the mountain from his house during the day, he measured what the globe would predict as well during the day. But the thing is, the star gets occluded at night at that physical location with the flat Earth prediction, showing that when you remove the refractive conditions between you and the object, that the elevation angle is true to the flat Earth prediction. That's the significance of what's being put forward with the concept of the celestial theodolite.
I don't know what a celestial theodolite is. So
yeah, so yeah. So I'll break it down for you. It's no problem.
You have one or what?
Yeah. So the celestial theodolite is when you it's when you use any mountain peak.
I'll show you mine and.
Please don't interrupt and play this like, do you have one game when I'm literally explaining to you how.
Yes.
Please do not do that. I'm trying to explain to you how you can make the measurements of timing of when it gets blocked by a physical object with known elevation to determine if that elevation is true to a flat Earth prediction or a globe Earth prediction relative to your distance away from it. So conceptually, right, we can think outside of, just we don't have to have the thing in front of us, right? We can conceptualize something, right? So what I'm putting forward is that instead of using a theodolite on the ground to make the measurement with the crosshair, we're using the mountain peak as the crosshair. And we're using the time in which we no longer see the star versus when we could see it to confirm that intersection angle, which would tell us if the mountain is physically at that location, which would correspond to a flat Earth or a globe prediction based on the timing that it gets blocked. So when you say, do you have a celestial theodolite? Can I go get one? That's really irritating because that's not what we're putting forward. So try and just try and be professional, man. Yeah, try and be professional.
Dude, anyone can go create a celestial theodolite, replicate these measurements as our boy Dr. Mike just did actually at 7 subsequent peaks, right? He made other measurements just to appease people. He went to Blue Mountain, Cheyenne Mountain, Mount Rosa, like Lone Pine Peak and Blodgett Peak, and the same result, same calculation, same flat Earth trig, proving true every time, regardless where the observation was made. So,
and real quick, real quick, just to address something in the chat, belittles like. He asked him how he took the measurement. It's a concept, LOL. We told you specifically multiple times how the measurement's made. It's done with timing. When you can no longer see the star, you record the timing, and then you go and confirm the angle in Stellarium. So that is how you make the measurement. You just confirm the timing. So when you repeat things like concept, you're, take a seat. Anyway, what were you saying, Kat?
Alan?
Yes.
Shane, we have like over 40 people in the room now. Can we maybe go back over some of the visuals and the whole celestial theodolite observation? Because I think there's a lot of people that weren't here at the beginning to actually hear this, to see the visuals that we have that really lay this out nice and well.
Absolutely.
Yep, probably. But nobody cares where the star appears to be, which is why we've eliminated refraction. Nobody cares where the star appears to be. The only thing we care about is what time did it get occluded by the peak, right? That's why we're eliminating refraction. That's why the angle from which the observation was made doesn't matter. It only matters that matches the calculation.
Yep. Yeah, so using. Oh, sorry. We'll let Taylor go ahead real quick because I did actually want her to come on and talk about the measurements during the day and the refraction thing real quick, and then we'll go to the celestial theodolite recap and show it all again, how it conceptually works. Go ahead, Taylor.
Yeah, I was just saying, Dr. Mike Heffron probably utilized the problem-solving skills that he learned in his education in order to think of a new way that we can get rid of like refraction when we're taking these measurements. So I'm pretty sure we can all like acknowledge that based on the atmospheric conditions, we can get different readings. I don't think anybody would contest that. I did post a link. I actually had to break the link in half because it was like too many characters. But it's a link. Basically, it goes over the temperature gradients of the nighttime versus the daytime, and how at nighttime, basically, those temperature gradients will even out and allow for much different readings. So like there was multiple studies that have been done before showing that, throughout the day, things will actually progressively get shorter. They did one a couple of them mountain ranges in New Mexico. They also did tracked like a hospital. These are all peer review papers. If anybody wants them, just DM me. The links are actually too long to post, so I could break them in half. But anyway, so this has been measured multiple times, and so I do recommend if you are doing theodolite measurements to like do them at different times of the day and different times of the night in order to get that accuracy in the measurements.
Yeah, so we should just go live, and I'll do them at night.
Yeah, that'd be cool.
Yeah, do them at night, and also do a
join live.
Can you do a celestial theodolite prediction at night as well? Can you?
Sure.
Because what we really need, honestly, bro, what we really need is a globe earther to take it upon himself to do the flat Earth prediction and the globe Earth prediction, and go out and measure the timing that corresponds to the globe to show that the globe is substantiated. Because right now, no one has even attempted that, and it's all been obfuscation and like not understanding the actual argument.
Yeah.
So I think it would be extremely helpful if you, since you offered to go and do those measurements, if there's a peak or something that we could help you calculate the stuff for and do it, like we would love to help you and work with you on that.
Let's do it live right now.
But first, could you steel man the argument that we've made thus far in any sort of form or fashion, please?
Yeah, what you're saying is that the theodolites prove that the Earth is flat.
No,
yeah, I knew it.
That they use a flat baseline, and that it aligns with flat Earth.
Were you saying that the angles of the stars correspond to a flat baseline, and that's proven?
Right. And so let me ask you, what is this flat baseline that you guys are talking about? Like,
I
where
have a
is
question
that?
about that for you, by the way. Do you use spherical geometry or Euclidean geometry whenever you do like your calcs?
Do what now?
Speaking of flat baseline, I was wondering, like, because
where
actually
is
one of the criticisms that I heard the other day for the quote unquote celestial theodolite was that they're not using spherical geometry, and I was like, oh my gosh, I have to go tell the Globers this, because I'm pretty sure pretty much all of them use the Euclidean formula. So anyway.
Yeah. So what is the flat? Anybody? So when I set up the instrument, like where is the
answer?
Where is? Yeah.
Okay, thanks.
Yep.
Yeah, I get it. I think it's fine, like you use Euclidean, that's fine, but it's just kind of funny, like, to talk about a flat baseline whenever, like, you're using, like, Euclidean geometry, which assumes a flat baseline.
So again, where is it?
Just outwards horizontally from you. Looks like you know how you think the horizontally things drop away from you and go curve.
Mm-hmm.
So instead of that, it would just be flat underneath you.
Where do I get it from?
What do you mean when you say that?
Like, where is it? What part of this equation?
Oh, got you. So that's going to be your distance. So when you take the distance to the mountain peak, right, that's going to give you the...
So show me on that picture there.
Yeah, I got it up right here. You can see it. Mm-hmm. So the distance...
Point to it.
Distance, 5,700 or 50,700 meters, or 57.7 kilometers. That's our distance from our observer peak, or from our observer to this peak, right? And our observer altitude is 2,074, and the peak of the mountain is 4,300. So we subtract these two here to get our difference in altitude, which is 226 meters. We have our distance for our flat baseline, which is 50,700 meters. And that's going to give us an angle of 2 degrees and 31 arc minutes to that mountain peak from our 50.7 kilometer distance.
Right. So you do know a flat baseline is just the eye level in the instrument, right?
Ooh, so here's the thing, bro. If we do the same calculation for what the elevation...
See it in a book?
No. Just check this out, though. So if we do the calculation for the globe, right, and we take the distance over the radius of Earth, we get a calculation that comes out to be 2 degrees and 4 arc minutes. So we have two different predictions for the physical elevation of the peak. Now we can get into refraction to refract it up and say that, it's up here or whatever, right? But when we make the prediction for the globe, we're accounting for globe slant, for how much is going to be deviated from it relative to us. due
What do you mean?
to Earth curvature. So that mountain peak is going to be lower than what it would be if the Earth is flat because it's tilted away from us relative to our position, right? Because of the curvature between us.
Right. So how much would it be tilted away?
Good question. It comes out to be 27 arc minutes. So you subtract 27 arc minutes from the raw flat Earth prediction, which was 2 degrees 31 arc minutes, which comes out to 2 degrees and 4 arc minutes.
I'm checking.
Mm-hmm.
Can I ask a question?
Absolutely. Go ahead.
How much did you get?
For which? For what? For what?
For how much it's leaning away?
It comes out to be 27 arc minutes.
Yeah, I got 27 minutes and 19.4 seconds.
Yeah, 27 minutes. Yeah, that's what I got.
How would you measure something like that?
How would you measure something like that? Great.
How would you measure something leaning away from you?
Great question. So if there was a star that was above the peak, and then when we physically didn't see the star anymore, we could take the timing in which the star was physically not there anymore, and we could confirm where that star would have had to have been to be physically blocked by that, and we can determine which of these angles is correct.
Okay. So you would then take your celestial theodolite.
Dude, is there a horse eating an apple somewhere or what? Like what's
Yeah,
going on?
yeah, hold on.
Here?
Yeah, someone has to fix their mic. Sorry, it's that person, the real Ainsley. Sorry, go ahead and continue, Baron.
I don't know who that is. All right, so you take your. Oh, that's what I wanted. I wanted to see the guy's actual, like a screenshot of the measurement of the angle. You know, like the vertical circle or the,
You're muted, Alan. And it's confirmed in Stellarium. That's the final vertical cross.
Yeah, so the measurement is confirmed based on the timing. So when the star is no longer seen, that's where we get the confirmation of the angle, because that's where it's physically blocked by the mountain peak. So we're not concerned with like refraction or like where it's being lifted up. Can we still see it? Where is it at behind the mountain peak? None of that matters. It's when it gets physically blocked. So it gets blocked at 6:27:25 p.m. Mountain Time on January 31st, the star 39 Aquarii. And then so with that being blocked at that angle, we can confirm that if once it gets blocked there, you can consider that like you're being instantly teleported from your observer point here to this mountain peak. And that's what is showing, that's how we're continuing this baseline here. So we're saying that this is the confirmation that these elevation angles are with respect to a flat baseline. Whereas if it was a globe, the timing that it gets blocked would be different, and it would be it would be significant globe evidence.
Interesting.
Because the difference comes out to be like 16 to 18 seconds in in timing. So even if you were off by a second, for user error or what have you, it's still a significant difference from what the globe predicts. And then they actually make an additional prediction. So when you get instantly teleported to the peak of the mountain due to ball being underneath you, the star angle is actually going to increase by your refraction amount that you're going to have to add. And what's really interesting about that is when...
Yeah, how much refraction would you add there?
Okay, so there's two different ways that you can do this calculation, and they both give the same result. Do you know... I don't know if you know who Ruhif is, but the way that you can calculate it to get the what the prediction would be to use terrestrial refraction, the calculation comes out to like 2 degrees and like 14 arc minutes or something like that instead of 2 degrees and 4. And then you add like 2 arc minutes for terrestrial refraction. The way that we're doing the calculation and how it comes out is we're adding celestial refraction to it, which gives the same result for we both make the same prediction, just getting there at a different way. And then when you go to the mountain, you would have to use the celestial refraction anyway for the 15 arc minutes. So that becomes the same. So like we have a slightly different route to get to the baseline prediction, but when we get to the mountain, we're using 15 arc minutes for the celestial refraction from G.G. Bennett, 1988.
Okay, so my question is that I heard you a moment ago say that you agreed or it sounded like you said you agreed with the 40,075 circumference of the equator.
Yeah, sure. It's
It's,
it's relative to the coordinate system that's being used by, because in order to even do geodetic surveying or anything like that they tell us about, you have to actually assume and know the dimensions of the Earth. So when they do things like Eratosthenes and they're like, oh yeah, he confirmed it. Well, he would have also had to have his own set of geodetic surveyors to even give his, predictions and all that stuff. So it gets rather circular there. But yeah, relative to using the coordinate system, and its applicability, you could say that those are the dimensions. I don't think that those are the exact dimensions, right? But calculative computation wise, that's what we're using. I agree to that. No problem.
if you were going to change them, what would you change it to?
Oh, nothing. I wouldn't change anything about it. I think that the only way, because when you go through the process in which the map was actually built, we would have been doing the same thing, assuming that we see in a hemisphere of vision rather than we see in a hemisphere of vision due to the ground beneath us being curved. Everything that they mapped it out and the corrections, etc., would be the exact kind of thing. And then so the difference being between the two models really is that they conceptualize the stars as being like physical locations and like physical objects that you could like make a triangle to, whereas our position is that they're apparent objects. Everyone sees them slightly differently. So if you try to cosine to a star and take a measurement of the distance there, and then you take a zenith measurement after you traverse the distance, that star is never going to be directly in the center of your telescope when you look up. It's always going to be off a little bit, and that's not due to Earth curvature. That would just be due to everything is in an apparent position, and that's the only difference really. They just kind of told everyone that the reason that it's in a different position is because ball curve slant.
So it's rare that I run into somebody who is confident in stating that circumference at the equator is 40,000 kilometers.
It's a computation. No one's ever measured it, right? But it corresponds to the usefulness of the coordinate system. Yeah. Jane, actually, do you want to do a quick little screen share of an Eratosthenes breakdown? You want to do I could bring you up on the big screen and then we can close out because we've been going for an hour and a half.
Yeah, I was trying to go to bed, but yeah.
Yeah, I got you. And then if Baron wants to round us off after he's done calculating or whatever.
But all right. Well, real quick though. So 360 degrees divided by 7.2, which is the angular difference in the supposed parallel light. The difference between the well and Syene and Alexandria, right? And Syene happens to be at the Tropic of Capricorn, so he's assuming parallel sun rays. He's doing 360 divided by 7.2 times 800 kilometers known distance between Syene and Alexandria. The only way that circumference has any value or ties to the Earth is that distance has to be accurate. It has to be the ratio between an arc length of that same circle at the same segment. So the way that they proved it was by knowing the difference and then knowing the distance. If you look into it, they said they hired Bamatis, which are like special geodetic surveyors that's supposed to look into how they definitely measure the distance. But actually, if you look into it further, none of that happened. They were never confirmed. It was never actually a known distance. They said that they just referred to old maps and old geodetic surveys. So they effectively measured the Earth by already knowing the Earth. And it's the only way the circumference gets measured is by knowing that known distance. And it was only known by previously known measures, hence the first geodetic survey. But when you're going to talk about the distance traveled on an arc length of a circle, you're going to apply it to a sphere. We're just going to apply it to, say, that equatorial circumference. And then you can make the same sort of deduction based on how far the sun would travel laterally across that arc length for 15 degrees, with the same known distance, keeping the equatorial circumference in mind. There you go.
So I love Eratosthenes, but it wasn't the purpose of my question. My purpose of the question was to ask the next question, which is if that we have a radius of 6,380 kilometers, and then we add another concentric circle because there's stuff below the equator, and we just double it. That takes the radius from 6,380 kilometers to 12,760 kilometers. And it takes our circumference from 40,075 kilometers to a circumference of 80,170. Now, everything that's on the north side of the equator, calculations work no problem. But if we have a doubling concentric circle, moving out, then distances seem to not work from reality. And I'm asking why you think they don't.
Well, that would be assuming that we're measuring distance by how visually skewed it is at the outermost edge of our azimuthal equidistant projection, which of course is a flattened out spherical graticule, right? If you refer to like Tissot's indicatrix, which is like the ratio by which map projections get skewed, the outer edge would form like the widest ellipse, even though it would mirror the inner circle at a perfect circle. And so the relationship there is that the distortion you're trying to measure would actually represent the same sort of symmetry as per the projection you're trying to put it on. That's the actual answer to it. The real question is the tropics different lengths? And the actual answer is we can only measure by referring to the same coordinate system and then performing the same calculation. You can do, cosine at 23.4 degrees to get the distance of the so-called tropic in each area.
Well, yeah, so the Tropic of Cancer, Tropic of Capricorn would necessarily have to be bigger than the Tropic of Cancer on a flat Earth, right? Like, it's just a necessary fundamental fact if the Earth is flat.
Well, I mean, for both calculating it based on angles to the stars to a known latitude deriving from celestial angles, then no, I mean, we would both calculate it the same way. I mean, I agree, but the better question would be how would we measure it in reality? And we'd have to find a way that doesn't calculate it based on angles to the stars. Because symmetry based on sky symmetry, of course, is going to come up the same. No matter which side you're on, 23.5 with the cosine is going to give you the same distance based on the radius, right? So it's all based on the coordinate system when you're calculating those distances.
Right now, direct flight from Chile.
All right, I'm gonna go to bed. I'll see you guys later.
All right, later, dude. So to answer your question, the coordinate system is symmetrical. When you're looking at an AE projection, it looks distorted. It's all, looks like, whoa, that's crazy. These distances can't match. They're symmetrical. It's the same distances that they are in the north. You can go to ADL.place and go to, what would it be under? Flight routes? Yes. If you type search you go to ADL.place and and click on Shane's database. And then in the search box, type flight routes. You can see all the transformations and flight routes and how they look skewed, but they're the same distance and all the math to go over that to answer your question. So it's kind of like it's a non-issue for us. Baron, we got 7 minutes left. Do you have any more celestial theodolite questions or follow-ups or anything like that you would like to get to before we close out, sir?
Yeah. Where do I buy one?
All right, dude. So
you can buy a theodolite on Amazon.
Yeah,
a celestial theodolite on
Taylor. Be an adult, bro. We're sitting here asking you to participate in this measurement, be helpful, score one for the globe, be the hero, refute our measurements, and you say, where do I buy one, bro? We told you explicitly you can use any mountain peak you want and a fucking stopwatch, bro. You just use your phone because it'll have the timing, but yeah, that's how you do it, man. So what you're doing is very immature and not helpful to anyone that's actually trying to get understanding of the argument or have clarification. You say because it doesn't exist, yet we have timing measurements that correspond to the star being blocked by the mountain peak. So now you're just lying about measurements. How would you feel if I started saying that your theodolite measurements didn't exist? That would be retarded, right? So really let that sink in and look at that juxtaposition of what's happening right now. You don't have anything, yet we have entire data tables of it, bro. So enjoy.
Thank you, Alan.
Yep.
I did have a question before we head out. First of all, like I said, the other day I had a really unique piece of feedback for the theodolite conversation. They were talking about it, and then they were like, "Oh, well, did they use spherical geometry?" And I was like, "Well, no, they don't. They don't usually use spherical geometry to make accurate the globe prediction. Usually, they use the Euclidean, and they take the drop over distance and see how much angle that would have deviated from the flat versus globe." So then I was wondering, is there actually a way to do spherical geometry for the theodolite calculations? And is that something anybody ever does?
I think that 8 inches per mile squared did it on one of our lives. The first time we brought up celestial theodolite, I think at the end he calculated it that way, if I'm not mistaken.
Dude, that would be the first person I've ever seen do it.
Well, Eric also did ECI to ECEF transformations for everything, so we could just ask Eric for his calculations. You can see what he did because that would be all sphere trigged out as well.
Did Baron leave?
Oh, cool. We got violated for hate speech. Could result in your thing being terminated.
They immediately reported you because you said the R word. I knew it, dude. I knew as soon as you said it. They were like, "Oh, I can't be associated with it. Let me virtue signal my way out of here. Maintain my dignity. I'm out. You guys suck. We win. Superior."
Dude, no worries. A grown man just said measurements didn't exist. I mean, that's the pinnacle of where we're at argumentation wise. So I can totally understand why they have to do that.
Yep.
Taylor, they kicked Baron. Did we kick Baron?
No, I think he left and reported us.
When somebody gets kicked, it says there's like a highlight thing on the thing that I'm streaming. So if he did, it'll be on there or whatever. But I didn't see it.
I already closed it.
And I never hear any of them. I never get much feedback for like the fact that things get triggered during the day. Like it seems like they just like brush right over it. Like it doesn't seem like it's addressed much. So.
I kicked him. I kicked him.
Oh.
Because he said once again, like a child, he wanted to like know where to buy this.
Right. Oh, I thought he said that and left.
So that you could continue.
Yeah. To be fair,
I did kick him.
To be fair, if he didn't leave after that, I would have kicked him because that's the end of the conversation. So I didn't see that. I thought he left.
Kicked him so you could finish.
No worries. Cool. So yeah, if there's nothing else to contribute to the conversation other than the measurement doesn't exist, where do I buy a thing that you already explained how it works, and I'm just going to ignore it, then like there's nothing really to contribute. So yeah, peace be upon you, brother. So anyway, let's see. I think Liliana. Is that the brush tail babe? Are we about to get a brush tail ad? No way.
Hi. Yeah, what's going on? I just joined. I was upstairs in the kitchen doing kitchen-y things.
Nice.
What's new here?
Do we have a celestial theodolite? Do we have a pair of binoculars and a clock? Yes. It turns out everyone has a celestial and a physical object to occlude a star, so a mountain peak or a building, literally anything. So to answer the question, do you have a celestial theodolite? If you have binoculars, an object in the distance to occlude stars, and a phone or a clock, you're good to go, it turns out. How about that? Turns out everyone has a celestial theodolite if they really want one. Binoculars to take precision measurements. Oh no. Too bad it's about the timing in which you no longer see it. And you can do plus or minus 1 second and it's still not going to be, the globe is much bigger and different. So it doesn't matter. So even with the inaccuracy of plus or minus 1 second, doesn't matter. So while you're mess around in the chat, that's cool, man. We're just going to ignore actual measurements now. Sweet. So the position for the globularist isn't that the timing's wrong. It's not that the calculations are wrong. It's that the celestial theodolite doesn't exist in, what was the other one? Crazy, dude. Okay. So anyway, Lily, do you want to wrap us up with an ad?
Yeah, I was just going to say, I don't know why they don't understand that the timing is a really like the most crucial factor in this whole thing that, Dr. Heffron taught us. It's all about that moment, that time that the star disappears.
Exactly.
From our view, right? They just don't get it. I don't know why.
That is the significant part. Well, it's hard because once they get that part, it's over because they predict a different time. And once they understand the significance of the timing, they can't be like, oh, but coincidence, because they have to say either it's a coincidence or we got the timing wrong.
Yeah.
And they're not even doing that. They're just
too many times for it to be coincidence.
Yep.
Yeah, I got a brush tail ad. You want me to finish it off?
Send it, Lily.
Oh, yeah. So this is a very interesting testimonial that I haven't told you guys yet before. Another miracle of brush tail coffee. So what happened was late last summer, I was sitting under this beautiful apricot tree that I have in the yard, and for some reason it had just never been producing fruit for the last 4 or 5 years or whatever. Anyways, I couldn't understand it because it looked like a good healthy tree, etc., etc. Long story short, so I was sitting there under the shade. It was summertime. It was already warm and hot, by 9 o'clock in the morning. And then I was drinking my brushtail coffee. And then just by accident, when I set it down, a bunch of brushtail coffee like spilled out of my mug. Anyways, so then I went back inside and everything. The next day, the tree was full of blossoms. And then there was just swarms of bees. And then within a week, there was fruit on the tree. Loads of apricot. I was making dried apricot, apricot jam, apricot leather, apricot this, apricot that. Oh my God, I gave so many apricots to my neighborhood, people in my neighborhood. Anyway, long story short, people, you can expect miracles from brushtail coffee. I think the tree really enjoyed that coffee I spilled, and that it just went to town with the blossoms and the fruit. Here's the magic of brushtail coffee at brushtail.coffee. Is that the website? Brushtail.coffee.
Nailed it, Lily. Brushtail.coffee. Thank you so much for your contractually obligated ad read. You're such a good and valued member of the Ether Cosmology Corporation.
Well, thank you, sir.
All right, lads and ladettes, tune in to, let's see, what do we got coming up this week? Today is Wednesday. Tomorrow is Thursday. Oh, dude. So for those of you who are able to venture outside of TikTok, tomorrow on the Clubhouse app, if anyone's a Clubhouser, if you go to Flat Earth Gang or hashtag Flat Earth Gang, I think it is, at 8:30 p.m. Eastern, Dr. Mike Heffron is going to be doing an interview on the celestial theodolite. And if anyone has any questions, refutations, they want to come and call him names, something like that, be there at 8:30 Eastern tomorrow. We'll be going, he'll be having an interview there on Clubhouse. I'll be streaming it on YouTube. So if you don't want to venture to Clubhouse and you want to watch it on the tubes, go to YouTube, type @space_audits, and that will give you the stream for that. And let's see what else we got. So Friday will be a Twitter community event. And then Sunday will be Globebusters, where I'll be going over inertial forces and where to find them. All right, lads and ladettes, take care. We're going to close it out. Have a good night, everyone.
Are we going home now, Alan G?
Lily, we're going home. I'll see you at home, Lily.
Thank you.
Much love, all.
Later.
Yep, lots of love.
Are we going home? Dude. All right, Lily's hilarious. All right, YouTube lads, to the lads and ladettes in the chat, thanks for holding it down in the streets. See my boy Gally in there dancing. All right. See you guys tomorrow.